we will conclude this lesson with a corollary to Green's theorem. It states that the area A of a region R bounded by the positively oriented piecewise smooth simple curve C is given by one of three expressions: 1/2 times the integral around C of minus y dx plus x dy, or just minus the integral around C of y dx, or just the integral around C of x dy. So why is this the case? Okay, a corollary to a big theorem like Green's theorem is often something that you can conclude fairly quickly from Green's theorem or from the initial theorem. So here, I want to remark that the area of a region, which is supposed to be an area of the region R, okay, it should be that A is equal to a double integral over that region of just 1 dA. So we saw this previously, that if you integrate the function 1 over a region using a double integral, that should give you the area of that region. So we want to apply Green's theorem, though. So if we want to apply Green's theorem, we need to apply the right-hand side of Green's theorem to that double integral. So to use Green's theorem, we need to find a vector field, PQ, so that dq dx minus dp dy is equal to 1. So here, what we're going to do is we're going to look again at Green's theorem, which is the curve integral of f dot dr around a closed loop is equal to the double integral over the region of dq dx minus dp dy dA. And so if we know that dq dx minus dp dy is 1, then what we have on the right is the area of the region R. And then what we're going to do is we want to convert that to an integral around the boundary of f dot dr. Well, essentially, I can give you 3 different examples of a vector field PQ so that dq dx minus dp dy is equal to 1. Those examples are, we could let P be minus 1/2 y and Q equal 1/2 x. In that case, if we take dq dx minus dp dy, we get dq dx is 1/2 minus dp dy is a negative 1/2, and that equals 1. And so if we set up the left-hand side of the integral with p equal to negative 1/2 y and q equal to 1/2 x, then the integral of f dot dr around c is going to look like that integral. Well, that's just one option. Another option is we could let p equal negative y and q equal 0. In that case, dq dx, which is 0, minus dp dy is 0 minus a negative 1, and so you get 1. And so what that does is that gives us this option for the line integral of f dot dr. we could consider p equals 0, and then q equal to x. In that case, dq dx is already 1, and dp dy is 0, and so we get 1 minus 0, which is equal to 1. And so that case corresponds to this final integral. And so essentially, by applying Green's theorem to a vector field PQ, where dq dx minus dp dy is equal to 1, then we can set up that the area of the region is one of these three integrals. So let's see how this works in an example. So we're going to apply the corollary to Green's theorem to find the area of a region R bounded by an ellipse. So you may know the area of a circle off the top of your head is pi r squared. Okay, but what is the area of an ellipse? Well, one way that we can find out the area of an ellipse is we can apply Green's theorem, where we think about the ellipse as being enclosed by some curve C. So here I'm going to draw my ellipse. Okay. It's going to be enclosed by this curve C. Make it positively oriented. And so if I want to find the area inside the ellipse, I can apply the corollary to Green's theorem. So I'm going to have to parameterize the curve in order to apply Green's theorem. So here, r of t is going to be my parameterization of the ellipse. Okay, in this case, that's a cosine t, b sine t. If you quickly substitute for x and y in the equation x squared over a squared plus y squared over b squared, you do in fact get 1. The derivative r prime of t is going to be minus a sine t, b cosine t. And so in order to find the area of the ellipse, okay, so we want to know what is the area, which is the double integral, okay, over r dA. We're going to apply Green's theorem, which says that it's 1/2 times the integral around c of x dy minus y dx. So that's going to be 1/2 times the integral around c. Sorry, I'm going to now do the integral from 0 to 2 pi, because here t is between 0 and 2 pi, to give me the full ellipse. And then x is going to be a cosine t. dy, in this case, is going to be b cosine t. And then I'm going to subtract y, which is b sine t, times dx, which is minus a sine t. I'm going to integrate that dt. So I'm going to integrate 1/2 integral from 0 to 2 pi of ab cosine squared t plus ab sine squared t dt. Of course, we have that cosine squared t plus sine squared t is equal to 1. So we're going to get 1/2 the integral from 0 to 2 pi of just AB dt, which is a constant. So we're going to get 1/2 AB times 2 pi times the length of that interval, or pi AB. And that's actually what we expected to get for the area of an ellipse. Right? The area of a circle is pi r squared. We think of A and B as being the two different radii of the ellipse. Okay, so instead of pi r squared, we get pi times A times B.